London, England. At the heart of this sprawling metropolis lies one of its most recognisable buildings. Battersea Power Station. Nearly 100 years old, in its prime it supplied electricity to a fifth of homes and businesses in the capital. But for more than 3 decades, this once great cathedral of power has stood derelict.
Battersea Power Station is a really important, iconic building, partly because of the scale and size of it, but also its location right in the centre of London and on the bank of the River Thames.
But now, this legendary building is about to be reinvented, and Sarah Banham is one of the team facing the daunting task.
I think Battersea Power Station is quite unique. It's in a lot of films, music, it's instantly recognisable. But it has been called the Everest of real estate. It wouldn't have stayed empty for over 30 years if it had been a simple solution.
The plan is to radically transform this immense 260,000 square foot building on the banks of the River Thames. On the inside, the old boiler house, which is large enough to hold 4 jumbo jets, will become 6 floors of office space, plus apartments and an events venue. Either side of it, the 2 mammoth turbine halls will be transformed into retail space. Next, the 2 former switch houses are to be converted into over 200 residential apartments. Finally, the building's 4 iconic chimneys will be rebuilt. And inside one, a cutting-edge glass elevator fitted, allowing visitors to enjoy breathtaking views across the capital. Today, work is nearing completion on this ambitious billion-pound project. To turn this powerhouse of the past into a cutting-edge centerpiece of the city.
It'll be a whole mixture of places for people to live, work, visit, just come and explore. It will be phenomenal, and it will all be inside that wonderful, huge Art Deco building.
This is the biggest project that I have worked on, and certainly one of the most challenging for me.
There isn't just one building that's being built here. There are effectively 8 all rolled up into one massive project.
On site, project manager Nacho O'Leary has his hands full.
So we're now approaching the east elevation of the power station. This is the east annex wall. What you can see above us is all the new residence apartments, and this is the new glazing that we're putting in for the shop fronts that will be facing the phase 1.
The size of the project is astronomical.
So these are where the residents will be entering into, coming in through the landscaping from the side, using the lifts and then going up to their apartments above.
More than 2,500 workers must excavate the equivalent of 60 Olympic swimming pools worth of earth. Install over 25,000 tons of steel structure and replace 1.75 million bricks.
The redevelopment of Battersea Power Station is one of the largest projects going on in Europe. It's significantly complex in terms of the volume of work that we're undertaking and the number of man hours that we're working to, but also retaining the existing building and respecting that is a very challenging piece of work. Many people have tried and failed to redevelop the Battersea Power Station.
Since it stopped producing electricity in 1983, there have been many plans for what to do with this iconic building. There was talk of turning it into a football stadium, a place of worship, or even a waste incinerator. But these ideas all turned out to be rubbish. In the late 1980s, a group of developers planned to turn it into a theme park, and even went as far as ripping off the roof to fit in a roller coaster. But their plan soon went off the rails, leaving nothing more than a derelict shell.
I've been on here since 2013, right at the very beginning, so I know how complex it is. It is seen as a very impossible project to be undertaking, especially for those that aren't involved.
To repurpose this 20th century icon, the team are facing many extreme engineering challenges. How do you keep one of the world's largest brick buildings standing when it's slowly turning to dust?
The replacement of the 1.75 million bricks is quite daunting.
And ensure that it doesn't simply collapse when you start repairs.
This isn't just the biggest project that I've ever had to deal with, it's the most complicated.
How do you thread a new underground railway through one of the world's busiest subterranean environments?
This is one of the biggest challenges that London Underground has had for 30 years.
Finally, how do you transform a chimney into a world-class tourist attraction?
It has never been done anywhere before, certainly not at this scale or even attempted within a chimney like this.
This is the iconic Battersea Power Station. Located in the heart of London, it stood derelict for decades. But now, engineers are redeveloping this historic landmark into a pioneering new destination for the city. Situated at the heart of a brand new neighbourhood, this iconic building is being transformed into over 250 homes, more than 100 shops, cafes and restaurants. But first, engineers face a terrifying challenge, located on every corner of the building. The power station's 4 distinctive chimneys are an iconic part of the London skyline, but they're in a precarious state. Project manager Nacho O'Leary is responsible for finding a solution.
So the chimneys at Battersea Power Station are the iconic part of the building that people remember the most. When I first arrived, we had large lumps of the chimneys falling down from height at 107 metres high all the way down to ground level of where we are now. So because the chimneys were in such a bad condition, there was nothing further we could do than to take them down.
Piece by piece, the historic structures were carefully removed.
We employed a specialist steeplejack to undertake the works because the works are happening at such height.
In their place, 4 identical chimneys built from steel and reinforced concrete start to take shape. And to ensure they're indistinguishable from the originals, engineers have replicated the construction method used in the 1930s. Instead of using a pump, 25,000 wheelbarrows full of concrete are taken up over 160 feet in an elevator and poured into circular moulds.
So once the concrete's set, we jump the shuttering. And where that jump occurs, you can see where the horizontal lines are, every 4 foot.
Then, nearly 400 gallons of protective paint ensures they'll last the next 100 years. Now, the new chimneys are indistinguishable from the old ones.
A friend of mine asked why we hadn't replaced the chimneys. He hadn't realised that all 4 of them had been taken down and had gone back up and were effectively the same as they were originally. So I'm very proud that even friends of mine don't realise that I've done this work.
With the chimneys complete, engineers can now attempt the most ambitious part of the project.
The chimney lift is a really large passenger lift with an entirely glazed top. Public will be able to come in and get an incredible view across London from the top of the most iconic chimneys in the world.
For engineer Adrian Forget, it's unknown territory.
As far as we know, no one has ever tried to put any kind of lift like this within a chimney.
It's the chimney's unusual cylindrical shape that makes building an elevator inside the shaft especially difficult.
So normally a lift shaft is completely straight, but you'll see the chimney tapers. It's wider at the bottom than it is up at the top, and that's not normal for a lift shaft. You don't want your lift rails being anything other than completely plumb and straight, because otherwise you have problems with ride quality.
But the biggest challenge for engineers is how to pull the elevator to the top.
Because we're trying to give people a view from the top of the chimney, we can't have any of our equipment at the top getting in the way of the view.
A large motor at the top could also damage the chimney's structure.
The chimneys are designed to be chimneys. We are putting a lift inside it, which is heavy. The machines that operate it are heavy. And what we can't do in this lift shaft is put all of the weight, all the machinery at the top, because we know that the chimneys won't be able to cope with that.
It's a formidable problem to solve.
It has engineering challenges about every aspect of it, so it has certainly given me sleepless nights.
To find another way of pulling the elevator to the top, engineers need to look to history's great pioneers. Elevator manufacturer executive Patrick Hess is discovering the secrets behind an engineering masterpiece located deep in the Swiss mountains.
The Bürgenstock mountain is famous for its unparalleled views, and it's been a popular holiday location since 1872. So one hotel, the Bürgenstock Hotel, wanted to provide something unique to their guests. They wanted to provide a view from the summit.
And this was the result. This is the Hammerschwand lift. The top is 3,700 feet above sea level, making it the tallest outdoor elevator in Europe. But building an elevator on the side of a mountain presents a monumental challenge.
At the time, all elevators had the machinery at the top. But putting a heavy machine on top of a tall elevator shaft would make the structure too unstable. Who would be the engineer brave enough to tackle such a challenge?
Karl Loerle was a German bridge engineer. But in 1905, he built one of the most astonishing elevators in the world.
What a structure! In the 1900s, a truly remarkable undertaking and a huge engineering challenge.
The elevator shaft is a truss design, influenced by Loerle's railway bridge background.
To attach the shaft to the mountain, no scaffolding could be brought here. So builders had to upsail, like acrobats on ropes, in order to drill holes to make anchor points for the steel structure. Miners from Italy and Austria were brought in with additional expertise because the rock needed blasting with dynamite.
The shaft needs to be straight to ensure a smooth ride.
We think Loerle must have used a plumb line like this. It's a string with a weight on the bottom to make the shaft perfectly straight.
Loerle's outdoor elevator was a game-changing piece of engineering. But the real brilliance of the system is in the design of the mechanism.
This is the heavy machine which pulls the car up and down. After more than 100 years, it's now a new machine, but it's in the same place as Karl Loerle put the machine. It's on the bottom of the lift and not on the top.
At ground level, a large motor winds steel cables connected to a drum at the top of the shaft. As the system turns, the lift is raised and lowered as required.
This brilliant idea made the shaft more stable and is protecting the machinery from the difficult weather conditions.
The Hammerschwand lift enabled glamorous guests to reach the summit in just 3 effortless minutes. And this is what it was all for.
Look at this outstanding view.
For the past 120 years, the Hoffman elevator has provided one of the most scenic views of the Alps.
Carl Löhle, he was an engineering pioneer. He has made the impossible possible, and he has inspired elevator engineers around the world.
At the Battersea Power Station in England, engineer Adrian Forget and the team have taken Löhle's strategy to jaw-dropping new heights.
So we can just get ourselves into the lift shaft now. Lift shafts are normally very protected spaces, not many people get to go inside. So we're right at the bottom of the chimney now. So the machine is, I would say, the biggest lift motor you can buy. It weighs just over 7 tons. It produces 23,000 Newton meters of torque. This chimney lift is absolutely enormous, and that's why we need some really big equipment to get it moving.
Just like at the Hoffman lift, this monster machine is at the base of the elevator shaft instead of the top.
By keeping all the equipment at the bottom of the chimney, it means there's nothing up the top. That allows us to bring the lift right out of the top of the chimney. It gives people an amazing view across London from the top of the chimney itself.
The elevator is pulled up by cables attached to a massive steel ring at the top of the chimney. Cables run down to the motor at the bottom, back up to the top, and down to the counterweight. It's known as an under-slung elevator. But as the chimney gets narrower towards the top, engineers have also had to devise an innovative way to ensure the rails inside it stay straight.
So these are the rails that the lift car is going to run onto. We know that this chimney isn't completely straight all the way up, so we're going to use these brackets, which are adjustable, to make sure that we can keep this rail really straight so that we can give a really good ride quality as people move up to the top of the chimney.
To get people from the ground to the top of the chimney, engineers have designed a unique glass car. With capacity for 30, a ride to the top of the 109-metre chimney will take just 26 seconds.
The chimneys are iconic, and what we are trying to create here is a truly unique experience. I know that I am going to have been part of something incredibly special. I think we are going to, at the end of this, be looking on this as an absolutely wonderful feat of engineering.
In London, the Battersea Power Station redevelopment is one of the most astonishing construction projects on the planet. This enormous industrial icon covers an area over 260,000 square feet, equivalent to 96 tennis courts. Its steel frame consists of 8,000 individual sections. Around that, 6 million bricks form the walls of the structure, making it one of the largest brick buildings in the world. But having had its roof and floors removed over 30 years ago, engineers now face the task of finding a way to divide this empty shell of a building into homes, offices, retail, and event space. It's the biggest engineering challenge Michael Brooks has ever faced.
So the power station, when we arrived on site, was derelict. Lots of the floors were missing. The largest space between the 4 chimneys was entirely emptied. 150 metres by 150 metres by 60 metres tall, volume of space that needed filling. We needed to start putting in floors.
The team plan to install 14 new floors. The problem they face is that unlike the office and residential spaces at the top of the building, which can be supported with columns, the retail and event space lower down must remain open, forcing engineers to find another solution.
We've got a retail mall, we've got office space, we've got an event space, and all of these different uses have different structural needs. We can have columns, within an office space, but we don't want to have columns in an event space. How do we overcome that challenge? It is a seemingly impossible task.
To achieve strength on such an enormous scale, engineers will need inspiration from history's great pioneers. Urban planner Cara Michelle is in Bethlehem, Pennsylvania, uncovering a steel revelation that is behind New York's biggest skyscrapers.
In the 19th century, Manhattan's population was booming. And the only way to accommodate everyone was to build higher. By that time, buildings were already starting to get taller, but they were typically limited to about 20 stories. To construct a super tall tower, engineers would need super strong steel beams.
Luckily, one man was working on a solution. In the late 1890s, English engineer Henry Gray patented a new method for creating steel beams that were much stronger than those that currently existed. It was an innovation that would change skylines around the world, and it all started here. This is the former Bethlehem Steelworks, known as the place that built America.
The Rockefeller Center, the Chrysler Building, Madison Square Garden, even the Empire State Building all included beams made here. Bethlehem steel owners took a risk. Henry Gray's steel mills were new and different, and almost no one else was using them. But they bought the patent anyway, and they began manufacturing.
Gray's steel rolling mill could make beams stronger than had ever been achieved before. So what made these beams so resistant to bending? When a beam has weight on it, the top is in compression, pushing the steel, and the bottom is in tension, pulling the steel. By changing the shape of the beam, more steel is at the top and the bottom, where it's needed most, giving you a stronger beam.
I've got two beams here. They're both the same weight. The only difference between the two of them is their shape. This one is a straight beam, while this one is a wide-flanged beam. So we're going to put these two beams to the test to see which one is more resistant to bending.
First, the straight beam.
Already, I'm hardly putting any weight on it, and I can feel it bending underneath me. It is so flexible. I don't necessarily know if this is what I would want to have holding up my floors.
Now, the wide-flanged beam.
Already I can really feel the difference, and I don't feel that same amount of give underneath me. Actually, this is pretty impressive.
Bethlehem Steel's gamble had paid off. By the 1920s, its beams were part of 80% of New York's iconic skyscrapers.
Henry Gray was able to produce the wide-flanged beam better than anyone else had achieved. His bend-resistant beams made it possible to build tall, multi-story buildings, changing skylines all across America.
Back at Battersea Power Station in the UK, engineers are using bend-resistant steel beams to make 14 new floors. And one in particular needs to be able to take the weight of 8 new stories by itself. This gigantic beam is 27 meters long and weighs a whopping 62 tons. The unenviable task of manoeuvring it through the busy London streets fell to engineer Michael Brooks.
We had to run tests with lorries with brooms and ladders out the back just to make sure that we could actually navigate the length of the beam through the site.
It's one of the largest pieces of steel ever made in the UK.
It was picked up by the second largest crane in Europe with a capacity just enough to pick up this beam and install it in place. It was a very significant and obvious milestone for us. So here is the 62-ton beam. It is a super-sized I-beam. We have huge amounts of area of steel at the top and at the bottom, and not so much in the middle, and that gives us a high bending resistance. This 62-ton beam is super-sized because above it is an 8-story building with columns coming down that total over 2,000 tons with no columns underneath.
Located on the building's 5th floor, the gigantic beam supports the weight of the 8 stories above, leaving the event space below column free. Then, by adding 2 vast steel trees, engineers are able to create floors for the offices above, maximising the space.
These are the structural transfer trees. They're so named because we have one column underneath, what we call the trunk, and sprouting out of it are 4 branches that then divide again further up into 8 branches. And it travels all the way up to the underside of the level 5, which is where we have the office space above. Each of these trees supports 6 office columns, and by taking 6 columns above and pulling all of the load down into one central mega column below, what we've been able to do is create this grand space as people walk into the retail mall, and yet allow us to maximise the space for the office above. These are my pride and joy. They certainly are the jewel for me of the structural engineering on this project.
The power station redevelopment is well underway. But with no direct underground rail link to the site, the team still need to find a way for people to get here.
So with the regeneration of the area, there's going to be around 20,000 new jobs created, which will mean that we need a transport hub to bring people in and out.
For Jonathan Cooper, it will require some of the most complex engineering on the project.
We are going to build a new underground tube station at Battersea Power Station. This is one of the biggest challenges that London Underground has had for 30 years.
Engineers have formed an ambitious plan to dig a pair of tunnels almost 2 miles long, connecting the site with the existing Northern Line. To complicate things, this new section of track will pass directly underneath the Victoria Line. And where the old and new sections of tunnel meet, junctions will need to be created to accommodate the additional section of track.
We've got to connect the existing Northern Line, which is around 100 years old, into the new tunnel. This is really difficult because the tunnel that we're connecting into has to remain operational at all times.
The process starts with 2 650-ton tunnel boring machines being lowered 26 metres underground.
Watch the step here. So this is where the tunnel boring machines were brought down in 20-metre sections. They were put together and pushed into the launch tunnels.
Moving at 2 inches a minute, they grind through the London clay. Behind the boring machine, the freshly excavated tunnel is sprayed with concrete to create a reinforced lining.
It is very dark down here.
Roughly halfway along the route, engineers face the most precarious part of the process, tunnelling just 2 metres below the existing Victoria Line.
While we were tunnelling through this area, the operational service continued the whole time, and no one even knew that we were tunnelling under here. We're so close to the Victoria Line train here that you can actually hear the trains going above us when they pass. Right there.
After tunnelling for 9 months, the team eventually reached the site of the existing Northern Line. But there's one final problem to overcome. In order to tie the old line to the new one, engineers must connect the two with a junction. To do this, they dig a larger tunnel around the old one, revealing the original cast iron tube that dates back over 100 years. Next, a prototype machine lines the new larger tunnel, whilst inside the existing tube, trains continue to run. Then, with the train services halted for the weekend, the old section of cast iron tunnel is removed and the two underground lines are connected.
This is where the new tunnel joins with the old tunnel. It's pretty awesome to see a train running in the underground because it's a restricted area, and normally you can't see this. This has been the biggest project I've ever been involved in. I'm really excited about seeing it complete.
In the heart of London, Battersea Power Station is being reborn. Once an essential piece of infrastructure that provided electricity to the capital. After laying derelict for more than 30 years, today engineers are converting this iconic structure into a brand new neighbourhood, where future generations will live, work and play. So far, the structure's 4 famous chimneys have been rebuilt, with one of them transformed into a unique glass elevator that will offer visitors stunning views across the city. 25,000 tons of steel has helped to construct 14 new floors. And the London Underground has been extended by nearly 2 miles, giving Battersea its own station. But on site,
We've just got a ramp here, so be careful here.
project manager Nacho O'Leary still has one final crucial problem to crack.
Battersea Power Station is one of the biggest brick buildings in Europe. Over a number of years, the bricks have been exposed to the elements, water and also to wind. A number of the bricks that you can see have already defaced, just purely down to the lack of maintenance that happened for about 30 years whilst the building laid open.
In total, over 6 million bricks were laid by hand when the structure was originally constructed back in 1929. But more than 9 decades later, this ageing brickwork is presenting a problem for Nacho and the team.
Where we've had the water ingress come through, some of the damage has meant that a lot of the bricks are actually unstable. This is a prime example. It's got a lot of mortar around it and this crumbles away quite easily. The mortar is actually not holding the bricks in at heights of 56, 58 metres high. We're having to take out the unsafe structure to make sure that there's no damage to the builders below.
With the crumbling weathered bricks and mortar in the process of being removed, engineers will need to replace them with new ones. But this presents an enormous problem.
We think we need in the order of 1.75 million bricks just for replacements. So that's not including the new walls that have gone up, that's just replacing bricks that have been exposed over time to the elements.
But making 1.75 million new bricks that match the originals is a huge challenge. Engineers will need to look back to the 19th century for the solution. Archaeologist Cassie Newland is in Gloucester, England, exploring how an early brick production technique could help make millions of bricks for Battersea.
Bricks are absolutely essential in the Industrial Revolution. You've got all these infrastructure projects, you've got canals, you've got bridges, you've got housing, you've got factories. All those things absolutely depend on bricks.
The problem was that brickwork simply couldn't keep up with the enormous demand.
But making bricks is actually quite a fine art. You've got to heat it up really slowly, really gently, hold it at firing temperature for a perfect amount of time, and then cool it just as gently. If you do it right, you get something like this. If you do it wrong, you're going to get this. Bulgy, cracky, not fired properly, not structurally sound, absolutely no good for engineering. And it's a process you just can't rush.
Fortunately, in 1858, German engineer Friedrich Hoffman invented a system that would revolutionize production. Rather than using separate ovens to fire bricks, Hoffman's innovation used multiple interconnected chambers that allowed heat to pass between them, baking a vast number of bricks at the same time. At the Northcote Brickworks, their gigantic Hoffman kiln measures 130 feet wide, 64 feet long, and is capable of holding up to 264,000 bricks.
If we look in the ceiling, we can see feed holes. This is where the fuel comes in. Right at the beginning, in the 1850s, this would all have been coal falling down around the bricks. And if we look down in the corners, down here, there's a second set of holes, really low down. These are called the trace holes. And they are kind of the genius bit of Hoffman's invention. They allow you to use the hot gases from the combustion chambers, draw it through all of your other chambers to preheat those bricks. And that's why Hoffman's design is so cutting edge. It saves you time, because they're already preheated, and it saves you money that you're not spending on coal.
When one set of bricks is being fired, the chambers near it warm up too. So when the next chamber is fired, the bricks are already preheated. And when bricks are finished, they're kept warm, allowing them to cool slowly.
So we're now at the business end of the Hoffman kiln. That's the first chamber, and that's being set. The second chamber here, bricks are all in there. There's something like 16,000 bricks packed into that little space. And then you brick it off with these bricks, which is what you call the door. And then we go down to the third chamber, where the bricks have been sealed. You've had this sort of clay mixture put on it to keep all the air out, to make a decent seal. And then round here is where it gets really hot. Now this is all ready to go, and it is being fired. It's 940 degrees in here, and it will be kept at that temperature for another 6 hours. And it's really throwing out some heat. And now coming around this corner, this one's cooling down, making sure those bricks come out perfectly. And it takes about 3 days to get from a freshly fired chamber to cool enough to deal with. So I thought we'd have a bit of fun now with my thermal camera. Basically, blue colours are cold, and yellows and whites are like really hot. And so if I have a look at the kilns here, so the one I've got just here on the right of the screen is the one that's being fired currently. As you can totally see, it's glowing almost bright white, whereas the one off to the left is being preheated by all of those lovely exhaust gases, and the one further left than that you can see is just starting to heat up a bit. And then this side's the cooling side. So here's that kiln that's just finished being fired. It's super hot, and then as you move down the road you can see the bricks cooling, the kilns cooling, everything taking its time, making perfect bricks. And it shows so well on this thing. This is great.
Having a Hoffman kiln could increase a factory's production from 2 million bricks a year to 20 million.
Thanks to Hoffman and his innovative kiln, enough bricks could finally be produced to meet the demands of the Industrial Revolution. And because of the savings in time and in fuel, soon Hoffman kilns were being built all over the world.
Rather than invent a brand new 21st century process, engineers at Battersea Power Station have turned to this historic Hoffman kiln at Northcote Brickworks. The very same one that the original bricks for the building were fired in, back in 1929.
This kiln is so good that it is as efficient as a modern day kiln.
Dale Moss is in charge of producing 1.3 million of the new bricks required for the massive modern engineering challenge.
The Hoffman kiln is vital. It gives you variation. It enables the beauty of the brick to be achieved.
Unbelievably, most of the 1.3 million bricks are being made by hand, and Dale has an innovative technique to ensure the new bricks precisely match their 95-year-old counterparts.
We've developed our own weathering antiquing process, where we can age the bricks to match old buildings. So we weather them by putting them into water, into weathering fluids for various times.
The new bricks blend seamlessly with the originals.
Personally, making the bricks for Battersea Power Station is my biggest achievement.
Back on site, bricklayers are painstakingly laying new bricks to carefully match the original pattern. There are over 7 different types of brick and 20 different types of mortar. This mammoth task will take around 5 years to complete. But at the top of the building, project manager Nacho O'Leary faces another problem. Over 160 feet in the air, here it's too difficult, dangerous and time-consuming for workers to lay individual bricks by hand.
This is the east wall of the boiler house. We've had to replace the bricks that were originally here. There's about 750,000 bricks in this facade alone.
So to speed things up, the team created giant 13-foot square brick panels that can be lifted into place quickly and safely by a crane.
By using panels, not only was it easier for us to install and had less impact on other works going on, but it was a lot quicker way for us to actually mount the volume of bricks we had to the wall to form the wall itself. That reduces risk on site, and that's a massively significant point to flag when using panels.
This historic power station that stood derelict for decades has been transformed.
I'm very proud to have saved this wonderful historic building. Battersea Power Station is without doubt the most exciting engineering project I have ever been involved in.
It's been a privilege to work on one of the largest brick buildings in the world, and it's a very proud project for me to be involved with.
The thing that I think we like most about it is the challenge. The engineering skill behind it has been tremendous.
Inspired by the innovators of the past, by adapting their ideas, refining their designs.
I'm really excited about the opportunity to be a part of this project that will push the boundaries of structural engineering.
Engineers have breathed new life into this iconic structure.